Off that computer, I have my computer. Okay.
So, you guys turn it off. Welcome, everyone. Folks that are right there might be happier right here. Just if you're right, instead of being right in the corner, you can stay there. The one's right against the wall. Yeah, that's fine. All right. Yeah, I would just not be right behind this thing. Yeah, just don't be right behind the podium. But the ones that are right, just like the last. Yeah, just go down a couple more. All right, there's one there. You all can go back to that row there. Right now, you're good. I just don't want to be like, there might be something happening right here, and I want to make sure you'll be all right. And the salt and pepper, and the salt and pepper, I would use pepper too. You're going to use that one, yeah, they're so similar. Okay. All right, friends, are we all here?
Almost.
Excellent. Excellent.
Hi, how are y'all? Good afternoon. You have probably seen all kinds of things today, right? Did you look at brains under a microscope? Did you see some frogs? Did you get to play outside? I know playing outside might sound like a silly thing to do, but we all miss getting outside sometimes, right? And at least it was a beautiful day. We didn't have snow today. So let's hear from the different groups that are here. When I call your group, give me a little shout. Let's hear who's here. Where is Bethel? Hey, awesome. Hardin Park. All right, that was a good shout, man. Watauga Virtual Academy. Awesome. Naval. Davie High School. And Green Valley. I am glad that at this hour of the afternoon, y'all still have some energy left, because I promise you, you are going to be amazed by Jeff Goodman and his show. So this part of your day is going to be a science demonstration. You're going to see all kinds of things that will amaze you, and you're probably going to have 1,000 questions for the bus ride back to your school and your home. So that's going to be fantastic. This whole day is the STEAM Expo, and it is an official event of the North Carolina Science Festival. Did you know the whole month of April is dedicated to science in North Carolina? It is. It's really cool. There are all kinds of activities. So in the last couple of days of April, be sure to check online or otherwise and see what all kinds of things are actually available. Even this science show will be available online. We'll send a link out to your teacher. So if you enjoy it so much, you want to show it to your family or some of your friends, you can do that later. When the show is over, I will dismiss you in groups so you can leave with your teachers and go to whatever your next stop might be, whether that's headed to go get picked up on the bus or a few minutes outside. So don't jump up out of your seats as soon as it's over, although you probably will want to jump out of your seat when you see how amazing this show is. I'm going to turn it over to Goodman.
All right.
Welcome, everybody. It's so great to have you here. I teach science here. So I teach people who are going to be science teachers. These are some of my students. So Alexis and Howie, and Rebecca and Jordan. And they are all in my class where to learn how to be a science teacher. And one of the things that I love the most about science is how it connects everything in the world. And I'm going to try to connect up some ideas today for you and see if we can explain something by the end. It's a kind of explosion that you all have already experienced thousands of times today. Let me just throw that out. By the end of today, hopefully you will be able to explain an explosion that you don't even know you experienced, but you have experienced thousands of times today. If you come to my class, if you come to ASU or another college, it's probably be similar. You don't just watch me do stuff, right? So these folks are learning how to do it. And so they'll be helping me out today a little bit, or this afternoon a little bit. Today, there's a lot of people here. It's going to be hard to get you up on stage. I'll get a few people up to do a few things. But I guarantee, you come to college here, a lot of you are in 9th grade. How old are you? 8th grade, 7th? Sixth grade. Okay, so you're middle school. So 6 years from now, I'll still be around. I might be a little less hair if that's possible. But I'll still be around, and you end up in my class. You're not watching me. You're doing this stuff. Well, let's get started and see some of the stuff that you might learn how to do. So first of all, like I said, I'm going to try to build an idea that'll explain the explosion at the end. In the explosion at the end, there's going to be some motion. And I just need to real quickly get an idea of what you know about motion. Okay? So when something's moving, like if I throw this to Alexis, okay, how come it did what it did? Like what just happened? Somebody raise your hand if you tell me, yes, sir. I put force behind it. What else happened? Yes, right there. Yep. Ah, it made a sound. I love that. We're going to talk about sound today. That's a really good one. Yeah. Gravity was involved, absolutely, which is why when I throw it, it curves down. That's great. Anything else that's important? Yeah. Yeah. Ah, inertia. So it has the tendency to keep doing what it's doing, right? So if I run along and I drop it, it keeps moving a little bit. That is, if I put out a tray and I run along and I drop it when I'm even with the tray, does it fall with the tray? Does it blow backwards? No, it keeps going. So you all have done this, I'm sure, in your classes, but where you run and it keeps going because things tend to keep doing what they're doing. How come the beanbag doesn't move right now? How come the beanbag doesn't move right now? Yes, sir. Oh, but there's a force on it. Gravity's on it. Wait a minute, no, keep going. Ah, so there's no, well, just, I know what you're saying, but there's no unbalanced force. Okay, so Hallie and Jordan, come out here for a second. What I want to do is, I'm going to pull this over. You go to the other end. Okay, go to the other end there, Hallie. Push against the table, and we're going to push with a balanced force, right? Now, as soon as I stop pushing, it'll be unbalanced, and it'll move, right? So that's just the idea that if there's an unbalanced force, change its motion. Hallie, throw this to me. Ready? Okay, so I did that back. Why did it change its motion? Because I gave it an unbalanced force. I knocked it to the side. So things tend to go in a straight line, right? And now they're going to stay right there, and I'm going to swing this around. Now it's not going in a straight line. Why is it not going in a straight line? Why is it not going in a straight line? My hand's pulling on it. My hand is the unbalanced force, right? So when my hand is the unbalanced force, it goes in a circle. As soon as I let go, it's going to go in a straight line, right? So if I let go there, or there, or there, or there, it's going to go in a straight line. So where will it go? If let's say I'll swing it this way. If I let go there, where's it going to end up? Go ahead, man. I'm letting go of it, but it's right here. Which direction is it going to go? Keep going around the circle? You know what? I think we should make this a little more exciting. I'm going to swing it this way, and I'm going to let go of it right here. You'll come on out of the way. Okay, now, I'm going to let go of it right here. Is it going to continue around the circle out into you all, or is it going to go that way, or is it going to go back towards the wall? That way, you think, wait a minute, you're all ready. This is a beanbag. Get ready to catch it. If it comes around the circle, you're going to have to catch it. Ready? So, which direction is it going to go when I let go of there? It went straight, right? An object keeps going in a straight line unless it's acted on by an unbalanced force. And if it's not acted on by an unbalanced force and it's not moving, it stays still. So I said we we're going to build an idea. So let me just write this. Things keep doing what they're doing.
things, keep doing whatever they're doing, straight line, same speed, or staying still, doing what they're doing. Unless there's an unbalanced force. And I'm just going to say, unless, just to save some space here, I'll do unless, and I'll do it in a different thing, UB for unbalanced force, UB. Okay, we'll return to that. Okay, so I want you to explain, let's see, Alexis, would you get those set up for me, please? And come out here for a second, Jordan, or grab some water. I want you all to see, Alexis is going to hold this tray up. And Jordan's going to actually pour some water in here, right? Not halfway. Maybe to the top. You all see that that's really water. I mean, this isn't like some trick that, you know. Okay, so she's got 3 cups with water in there. Is there a force on the water right now? Yeah, what is the force? Gravity is the force on the water. How come the water's not falling? The tray is pushing up, gravity pulling down. They're balanced, right? So I was on a ship in off the coast of Turkey, country Turkey, and people were coming around serving tea on this boat, right? And they're walking around serving tea, and they have it on a tray like this, and they drink tea in Turkey. That's like the thing. I know people hear about Turkish coffee, and there is Turkish coffee, but they drink a lot of tea, way more. And they come around anywhere you are, and you know, it's kind of like a wavy, you know, ocean scene, and the guy's coming around, and the tea's not spilling at all, right? And in fact, every so often there's a big wave, and it, you know, comes around, and there's no spill. So what's going on? Why wouldn't that occur? Friction. So anyway, I like what you're saying. I like the idea of friction, but hang on just a second. I'm going to pour this back in here so we can act it out without the water spilling all over my head. All right. So when this thing was swinging, you're saying that when it's upside down, friction is keeping the water? Friction with what? I mean, like air frequencies? I mean, okay, I love what you're saying. If there's something moving, it's part of it. But let's get out of the idea of friction, because in this point, friction would be the friction with the base here, but when it's straight up and down, it's not friction keeping it that way. Only air resistance would be there. What do you think is back there? Okay, I like the word centrifugal force, but I've had hundreds and hundreds of people say centrifugal force and not be able to explain what it is. It's just normal, everyday explanation. Who wants to give it a real quick shot? I love this idea, and I see your hand up there. Shout out what your thought is. I like that idea. We're going to talk about it a little more. Yeah. Shout it out from the balcony. Okay, I want to combine several of these things that I said. Put your hand down just for a second. Okay, so when this thing is moving, it tends to want to go in a straight line, right? We figured that out. Keep doing what it's doing. When we say keep doing what they're doing, we're saying, you know, straight line or still or whatever. So if this thing were to go in a straight line, it would tend towards the wall, right? Well, what's in the way? The tray. Now it would go up towards the ceiling. What's in the way? The tray. Now its tendency is to go in a straight line up towards the ceiling. But what's in the way? The tray. All the way around, its tendency to go in a straight line is blocked by the tray. And that's what we call centripetal force, right? But in fact, what it is just things tending to go in a straight line. Now, if we take a look at this demonstration, I'm going to climb this ladder, and Howard, will you come over here and hand this to me, this cup? So these beads right here, okay? These beads, and now we'll shout steady back. This is a really, really good.
Is there a force acting on them? Yeah, absolutely. Gravity's acting on them, and the cup is acting on them, and they're balanced, right? That's why they're not moving. But if I pull them over the edge of the cup, now the cup won't be acting on them anymore, but gravity still will. Now I want you to watch really carefully. Okay, what happens? Okay, I'm gonna let them go, and I want you to watch what's happening up in here. Ready? We'll explain in a minute. Ready? Now, that's gravity acting like an unbalanced force on these things. So if you notice them rising up out of the cup, okay, why would they be rising up out of the cup? Why would they go up out of the cup? Okay, the way the other ones is pulling down, but these ones are going like, oh, you're like the ammonia is destroying love, unless there's an unbalanced force. Their tendency is to keep going straight up because that's what things in a straight line. They keep doing what they were doing until they feel that unbalanced force and it overcomes that motion upward. Okay, so we've got that things keep going in a straight line. Let's add it on by an unbalanced force. Now, I'm about to show you something that a friend of mine can't do. And the fact that she can't do it almost killed her. The fact that she can't do what I'm about to do almost killed her. Now, when I say that it almost killed her, we really thought she might die over a course of many months because her body wouldn't let her do this. So I'm going to come in here. Let's see. Jordan's going to help me. Jordan, just point to the level of the water. And Howard, will you come hold the chair for me, please? Okay. So the level of the water is right there. Okay. Now remember, this is something that my friend couldn't do, which she didn't want to stand on her head. But now go ahead. I'll grab my glasses on right here on my shirt. Just pull. Okay. Now she's going to give me some water. I'm going to mount around it. Okay, show them the level of the water. Okay, actually, I'm kind of thirsty. Okay, now, a cup of water is now in my stomach. But I thought we said things that are not moving, like the water sitting in my mouth, don't just start moving, especially up against gravity, unless what? Yes, ma'am. My mouth. Now, the person next to you, add to that. Yeah. Because my mouth is only the start of the business right here. What do you think? But with what part of my body? What's forcing it up? Ah, somebody said peristalsis. What is that? Oh, yeah, what is peristalsis? Up there, yell it out. What is it? Ah, but wait a minute, it was going up. Ah, moving it up. Okay, now I want you to come down from up there. Come down so you come on stage. Whoever said that, come on down. Okay. That person said, find their way down. Find their way down and up to the front here. So I want everybody right now to put your hand on your throat and swallow. Okay? That you're feeling muscles move. That's happening even in your digestive tract right now. What do you have for lunch? Sandwich. What kind of sandwich? Say again? Turkey sandwich. There's a turkey sandwich moving through your body right now. You can't feel the muscles doing that. Come on up on stage. You can't feel the muscles doing that, but it is happening. Yeah. Okay. So let's imagine that I ate, I don't know, I don't know. It could be either like blueberry juice or grape juice. Okay. So blueberry juice. Okay. Now, this is my stomach up here, so let me coil up my intestines here at the top. Okay? And I want you to use hand over hand and squeeze that up there. Hand over hand. There's go below. There you go. That's what's happening to the muscles inside your esophagus. and eventually in your stomach. Now, when you ever eat popcorn sitting on the couch for like, you don't have to get up every few minutes to do this, right? It just does it. You all have eaten lying on the couch. You go to bed, you wake up in the morning, you poop the popcorn out. It didn't, you didn't have to like jump up every few minutes to get it to go. You have muscles that are squeezing through your bodies right now. And remember, I said that was the thing my friend couldn't do. What do you think was wrong with my friend? What do you think? Yes, something was wrong with the squeezing. Her muscles stopped. So I want you to pretend, like I'll tell you when the muscles were stopped. Go, stop. They stopped moving at a certain place. The muscles didn't work, and so the food would stop at that point, and then it would rot, and then she'd throw it up. And that was it. She lost half her body weight. There are several ways you can get it going. One is with electrodes. They can also use drugs. They also have. In her case, actually the muscles work a little bit. She ate very small amounts of food. She learned how to eat these little bits, and she's alive 15 years later. She's okay. But here's an example. Thank you. Give my friend a hand. Here's an example of science being used to save somebody's life. Science isn't just for somebody to stand in a theater and say, oh, this is amazing, that's cool too. But the fact is that your cell phones and your cars and your bodies are all science instruments, and you are doing science every day of your life, whether you know it or not. Now, as we're doing all this stuff, we were able to see everything to build this idea. But I want to build another idea, which we're going to need later. And Alexa, can you hold this one? Okay, so, and this is that not everything that you experience in the world you can see. So Alexis has got this little hand there. You notice that when I push this down, the hand goes up. Okay, how come? How come the hand goes up? Yes, sir. There's air in the tube. Air is something, not nothing, right? And we can notice that when we have something, say, like an airzuka. Would you stand up for just a second? Because you got perfect hair for it. Yeah. Just stand up. Yeah, just stand up right there. So you'll see that if I aim this right, I gotta aim it right. Oh, there we go. There we go. Okay, so now I've got, stay where we are. I've got a bigger one that might work a little better. Okay, so okay, there you go. Now you can see, you will see in the back there that her hair is what now? There we go. Okay, enough for that. Enough for now. Now you can see that this thing is blowing some air out. Air is something, not nothing. So what shape is coming out of this thing? What shape is coming out of it? Yes, in the front there, yell it out. Top. A circle. It could be like a disc, look like a plate. Or could it, maybe it's a sphere. Could it be a sphere? Could it be? I think it definitely could be a sphere. Could it be a cylinder? Absolutely, it could be a cylinder. Might be a ring. How would we be able to tell though? How could you determine? Yeah. Put something, some kind of air that we can, a gas that we can see. Oh, I happen to have a gas that we can see, or at least droplets in fog. So what we're going to do is we're going to fill this thing with some fog, and then we're going to see what it looks like. Okay, so yeah, I need to. So remember, let's stand right halfway over the chair. So you go, take this one from me. Hold this. I just want you to remember that when I blew this, just hold it up like this. Just like that. Yep. When I blew this, it was, oh! Now let's, I'm going to do a gentle one. Oh, look at that. Oh, that's pretty good. Right? The same thing was happening when it hit her hair. we just couldn't see it before, right? Really good. Watch this. Watch. Be quiet for a second. Watch what happens when it comes through the room. You see how it's actually tracing air currents and it's rising. It looks like maybe they're, oh, I think that's heat rising. I think we're actually seeing the hot air down here coming up, and maybe the radiator, or the radiator's on, if you'll warm up. Somehow there's definitely rises up. That's cool. I didn't even know. Oh, they're good. Oh. All right. So, thank you. Give her a hand. Thanks so much. If air is something, I need the three electrons. That's top here. Bring that up here for a second. If air is something, that means that when you take a nice deep breath, and breathe out. Okay, that must be something that you're breathing out. Okay, so Alexis has brought me this thing that I call the leaky faucet. Okay, yes, you've got something to say. Well, that's a kind of a philosophical question, whether a vacuum is nothing. You know, the people who have debated this for a long time, but the idea is zero or something. That's an interesting idea. But there's definitely air in this room. We could see that there was air in the room because we saw it inside the tube. Now, what we're going to do here is we're going to show you what happens to the air that you all just breathed out if we make it really cold. So I need all of you to come on out here. Come on, my friends here. And we're going to pretend that we are the molecule you breathed out. What molecule did you breathe out? Carbon dioxide. Excellent. So we're going to be carbon with two oxygen, carbon dioxide right there. Now, should we be close together or far apart? What do you think? Far apart, because we're a gas. So you go all down there, you go here. Okay, now, we came out of a warm body. Should we be moving fast or slow? Fast, right? Warm. So if we hit each other, we just boing off. Boing, right? So we are a gas that is warm. Now, what if we wanted to make us into solid air? What should we do? Yes, sir. Decrease the temperature so we get going slower and slower, and we don't really bang off each other very well. When we hit each other, we might stick together until we turn into solid air. Now, how would we turn back into gas? Yes, sir, in front there. Yeah. Heat it back up so we start going back and we back out as a solid. Okay. So, I mean, as a gas, I'm sorry, from the solid. What I'm going to do here is I'm going to take some solid air that I have in this container here. It is at negative 180 degrees Fahrenheit, negative 80 degrees Celsius. And my friend Helen just gave me gloves. Why do you think I need gloves? Yes, ma'am. It's so cold that it would freeze my skin and kill the cells. So now I need, yeah, we're going to get two of these and we're going to walk them down. And yep, I'm going to drop some of this solid air, this very, very cold air, into this cup. And then my friends here are going to walk it down. They're even going to walk up into the balcony to show you what's going on in here. So I drop it in here. This warm water is wiggling fast. It's going to make these wiggle fast and jump back out into gas form. And you see it bubbling. And if you'll take that one down the row and then up to the balcony, same deal there. Okay. Now, while they're doing that, I want to tell you a couple of ways. By the way, this is, you know what this is, dry ice, right? You can buy it. Now, the thing about dry ice is that it can kill you. Let me tell you a couple of ways that it can kill you. For real. Like, just because you can buy it in the supermarket doesn't mean it's safe. Two ways that it's dangerous. Well, one, I've already told you, is about the third way is about not holding your hands because it'll freeze your hand. But that really would be more uncomfortable. You might lose your finger, but you wouldn't die. But I don't want this stuff in my car with all the windows shut for a really long time, because my car's going to fill up with what gas, though? Carbon dioxide. I don't mind if my car is filled with gas. In fact, I like my car being filled with vapor, which, as long as it is oxygen and nitrogen, and just a tiny bit of carbon dioxide, but it'll actually give you a headache at first, and then you fall asleep and then you die if you're in a sealed space that pushes all the oxygen out, because you need oxygen to burn your food and keep your brain alive. The other way that people get hurt, and this is really, in all seriousness, something you should know, you never want to put it in an enclosed container, a closed off container. This is not a closed off container because it's open on this end. But if you put it into a closed off container, it will keep making bubbles. It'll essentially do that in the air, and it will explode the thing that it's in will explode. And so, for example, if you put it in a glass container and put the cap on, shards will fly everywhere. And every year people get blinded by this, or will get killed, you know. So it's just really worth knowing that just because you buy in the supermarket doesn't mean it's safe. You gotta know what you're doing. But I'm gonna put it in here. I'm confident that we've got plenty of oxygen in this room. This is a small amount of carbon dioxide. I'm not too worried about it. And I'm gonna get some water and pour it in here, warm water. What's gonna happen to the solid air? It's going to turn into a gas, so we're going to start to hear this. And you hear it? Okay. Now I'm gonna here. You can hear it through the mic. Okay. Now I'm going to cap it off, but it's not capped off, and now it's coming out there. Now, so I'm going to bring that over here. Okay. And we're gonna take a little bit before we can. Whoa. Okay, let's when it comes down a little, we'll make some better bubbles. Okay, now those bubbles are filled with, what are they filled with? Carbon dioxide and water vapor. Okay, now Alexis, you want to try to catch some? They tend to pop. Now, Alexis, what does this feel like on your head?
Cold.
Yeah, she's actually inside a cloud. She's feeling the cold air. But yeah, it's a little hard to breathe in there because it's carbon dioxide. Let's get one more here. Okay, so that fog you're seeing is actually water vapor, and it's condensed from the water that is evaporating inside this tube, and then mixed with it is a bunch of cold carbon dioxide vapor. That's what's causing that cloud. Okay, that's leaking. Obviously, put that on. Thanks. All right. So what? I want to add up here, okay, is the stuff that we've been talking about. We've been talking about the fact that air is something. Air is something. We need these ideas. That's why I'm putting on the top of it. And also that when something gets warmer, what happens to its size? Yes, it gets bigger. So I'll write warmer is bigger. Warmer equals bigger. Okay. Now, let's think a little bit about what's going on with the sound that thing makes. Because remember, it's made of bubbles. What? So sound. What is sound? I want to make a note about sound. Somebody write it. Yeah. Vibration. Excellent. So sound is vibration. And I'm going to make a sound here by making this tuning fork vibrate. You all hear that in the back? It's going to be interesting to figure out why you can hear this thing that's vibrating up here. But it's a little hard to tell if this thing is vibrating just in the room here. So what I'm going to do is I'm just going to come to my friend who said vibrations, and I'll show you all a different version up there that'll be just as interesting. But I just want to make sure that you're able to, okay, see that I can actually make the water splash with the vibrating tuning fork. Now, this is a big room and you're not able to see it. If we have more time, if you come to my class, everybody gets to do that. But what I want to do to show you that sound and vibration is closer to this thing. Everybody put your hand in your throat. Just go bum, 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 bum. You feel that? Okay. Now, when I talk, I vibrate the vertebrae in the letters, and that's going to make this little mirror on the end of this can vibrate. And let me see if I can. Okay, now you can tell that my voice is making this thing vibrate, right? All right, so sound is a kind of vibration, and I can make stuff vibrate in all kinds of ways, right? What do you notice about these things? They're different lengths and they make different sounds. I need to get a group of people up here. Let me see if I can get, I need to just get a, okay, I haven't called the people back there. In the blue right there, will you gather 4 more people and have them come up front, please? You all are going to be involved in this. Please grab that one. All right. All right. So I want you all to come up, and we're going to intersperse you with my college students here. So you're going to come here, you're going to come here, and two of you can hop right in the end there. Okay, now, these folks are going to represent the air. We know that this room is filled with air, so if you're hearing a sound, we got to take into account what's going on with the air. And I'm going to be the tuning fork, or the vocal cords, either way you want to think about it. You're going to stand shoulder to shoulder, and I'm going to give a little pulse, a whack. The thing about air is it doesn't like to be near other air molecules unless you really make it get close together. They tend to spread out. You saw that when I pressed on that syringe and the hand went up. They don't like to be close together. So if I press on you, whack, it goes all the way down the line. Now, when it gets down to Howie, Howie's hitting the eardrum of the chimp. The chimp is hearing the vibration. Now, a vibration isn't a single pulse. What is it? A lot, right? Whack, 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 whack. It's not just whack. It's whack, 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 whack. So it'll look like this. Whack and whack and whack and whack. Okay, now, how can I change what I'm doing? How can I change what I'm doing? Yes. How hard I hit. What will that change in terms of the sound? What will that change in terms of the sound? Yeah, but in terms of the sound, what will that change? How loud it is or how quiet it is. So if I want to make a louder sound, if I want to act out a louder sound, I would do a harder whack and then another hard whack. And right. So, and the chip would be like, don't yell at me. Right? If I want to make a quiet sound, I do it. Now, there's another variable. What's the other variable for sound? Yes, ma'am. Pitch. How do I act out pitch with what I'm doing? I'll give you a hint. What am I changing? What am I changing? Yeah, that's what I'm doing with my voice, but what am I changing with my head? Somebody's saying it, frequency, it's how frequently I'm hitting, right? So a high-pitched sound, no, you were fine, you were right on it. A high-pitched sound is a more frequent whack. So if I want to make a high-pitched sound, I do whack, and then 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 whack, right? If I want to make a low-pitched sound, I would just do whack, whack, right? And of course, you can analyze anything I'm doing. This would be a quiet, high-pitched sound. This would be quiet. This would be a low, but loud sound. And this would be quiet. Okay. So I have here a straw, and I'm going to make it vibrate by cutting a little mountain into it. I know you can't see it very well, but this thing's got just a cut a point to it. Does anybody here play a woodwind instrument? What do you play? Clarinet. Clarinet has a single reed. This is like an oboe with two. Like so, when you go through it,
it makes a vibration, it makes a sound, okay? So I want you to think about what's going to change about the sound. Now, this. So what's going to change about the sound when I change the plane? Now, why did the pitch change? Yes. Okay, so it had to do with it getting shorter and vibrating faster. That's good enough for now. So the idea is that in an instrument, the longer the instrument is, the bigger the instrument is, the lower the pitch. Just like in real life, big dog, right? Big bird, little bird. Tuba, whoop, flute. Big person, get out of my yard. I'm sorry, Mr. Johnson, little person, right? Little people tend to have high pitches. Big people, low pitches. Mike Tyson is the one outlier on that because he's a big guy with a high pitched voice, but mostly that's true. Now, anything that I can get vibrating will make a sound. In this case, I'm going to get this thing vibrating in an unusual way. I'm going to heat it up, and there's a screen in the bottom, a metal screen. I'm going to heat that screen up till it's red hot. And when it's red hot, it's really good and hot, you'll see what happens that you can perceive from your own seat. Okay, so somebody's saying hot air, and you're absolutely right. Hot air, which is something, rises. Why does it rise? It's written on the board up there. Why does it rise? Yes, sir. In the gray, right there. Water is bigger, exactly, which means it's less dense and it floats in the same way that styrofoam is puffed out, if you think of it, less dense. So we have it right here. Sound is vibration. Is vibration, energy. Okay, and just to see if you're paying good attention, I want to make some sounds with this instrument called a theremin, and I want you to pay attention to what each hand does. Ready? So this hand can move this way. This hand moves up and down. Ready? I'm going to move this one up. What is this hand changing? Yes, in the green. Yep. The pitch, what? This is control the volume. Right? Now, this is a really weird instrument, and it's worth a whole demonstration just for itself. But I just want to say that it's an instrument you play by not touching. And I'm interacting with the electric field around these antennas. And as I change where it is, I wanted to play for my wedding. I wanted to have her let me play. She wouldn't let me, but she did let me play it for her bridal shower. So this is just a good example of me using electronic instruments still to create vibrations, and we can kind of analyze it along those same perspectives that we've been looking at, same ideas that we've been looking at. Okay, last couple of things, and then we can get to the big final thing that we're going to put it all together with. So I want to do something now that, again,
if you went home and tried it and got it wrong, you could do something really dangerous. So try to pay attention to what I'm talking about right now. I have 2 containers here, and one of them I'm going to do something in that you all have done before, which is just mix vinegar and baking soda. And that's not something that you can kill yourself with. It's just vinegar and baking soda. Okay. The other one, I'm going to mix bleach with hydrogen peroxide. Now stop and just listen for a second. There are things in the supermarket that you mix bleach with, they will produce a deadly gas, specifically ammonia or Drano, okay? So you never want to actually just randomly mix bleach with things. I happen to know that the bleach mixed with hydrogen peroxide will also bubble, okay? That's not a deadly gas. In fact, that's a very, very kind gas. Gas I really love. It's the gas. Well, you'll see. So what I'm going to do here is I'm going to get this splint burning, and I want to see what happens when I put it in each of these cups. Well, it gets kind of bright in there, right? But when it goes in here, it goes out. But when it goes in here, let's get it lit again, and we'll see what happens. So get it lit. Let's make some flame here. Okay, so this has got something in it that makes flames get brighter. Something in it that makes flames go out, but then they get brighter, but then they go out, but then they get lit again. Let's give it another little dose here. Some more. See if we can get that sucker. Oh, there we go. Up, goes out. What do you think this is? Carbon dioxide. Then what's this? Oxygen, exactly. So if I put a flame and some fuel and some oxygen near one another, we'll do this just one last time because we need this idea for what I'm going to show you in a minute. So if I put these together, then if things burn really well, if there's no oxygen, they go out. But if there's oxygen, you can actually get something that's not even flaming up to possibly come back to life. See if I can get it. There we go. Okay. Now, I want to write that down because we need it for what we're about to do. So we're going to say flame plus oxygen plus fuel equals fire. Okay, I think we've got just about everything we need. Thank you very much, Alexis. Now, yeah, I need that one on, and we're going to turn this whole thing, turn this whole table vertical. So, all right. So first off, I've got to just set this up a little bit by showing you this. And what this is a device that will pump parts of the world called electrons into, and let's see, where is my, there. If you would, Alexis, you can unplug everything out of the yellow thing and just plug that in and bring it over. So this thing right here will pump all of the electrons out of here and basically pump them into this. Electrons hate being near one another, okay? Take these off for just a second so I can show you what you're seeing. So if these 3 people were electrons, come stand right here. I want you to imagine that they despise one another, okay? And they despise one another so much that if they have anywhere to go, like for example, if I open up a place for them to go, Jordan, go down those steps and you're going to go all the way down the thing. Rebecca, you're going to go all the way over to the wall over there. They're going to get as far apart as one out there. They're like, we do not want to be near one another. Okay, stop for just a second. I don't want you to miss what's going to happen. So I'm going to put a whole bunch of them in the end here. And then I'm going to give them a chance to go back home. Now, what you're going to see is that there's a little belt here that's doing the pumping of these things, that they will actually jump through the air and make a spark. You'll see that up there. It's small, but it's a little spark. You hear it? Okay. So basically what I'm doing here is I'm pumping electrons into this thing, and then they're jumping back to this. Now, you can see that things that are the same charge, that is, things that are either positive, in this case, at the top of this thing, don't like to be near one another by doing this. Oh, take that on for me, well, just somewhere on there. So, since they don't like being near one another when they're the same charge, if they become the same charge, if I pump all the electrons away, they'll all be positive, they should stand up. Let's see if that's true. So, you see how they really hate being near one another. In this case, if I give them a place to go, they will gladly go there, right? So what I'm going to do now is I'm going to use that principle in addition to everything on the board to show you an explosion you've seen many thousands of times today. And I need to write one more thing. Electrons jump away. That's meaning away from each other. All right, thank you. So what I have here is I have a bottle. Now that bottle has two bolts that don't quite touch each other. Okay? They don't quite touch each other. Electrons are pretty good at flowing through metal. So if I give the electrons a chance to get to this bolt, they will jump into it. And when they jump through the air, what did you all hear? The spark, and you saw, some of you could see that little light. So that's going to happen. There will be a spark that goes to this bolt. But then they're going to get crowded. It's like I sent everybody to one place, and then they got crowded again. So they're going to get crowded, and they're going to jump from that bolt to the other bolt and make a spark on the inside. Follow me so far? So I'm going to make a spark to this one. They're going to get crowded there. They're going to jump to the next one. Okay. Now, I want to put inside this bottle some yeast pea. Alcohol. That's what alcohol is. You knew that, right? Yeah. Yeah. No, seriously. No, I'm not making this up, y'all. When somebody is drinking a beer or wine or whiskey, they are drinking the excretion, the pee essentially, of this little organism called yeast. It eats. Can you all see what that is right there? Can you see what it is? You see the word? What kind of alcohol? Grain alcohol, and that's a picture of corn. So this is something that started as solar energy, falling on a corn plant, turning into corn energy, corn stuff, right? That gets eaten by the yeast and peed out as alcohol, and I'm putting it in here in the bottom. Remember, you have seen this already today. You just haven't thought about it this way. Okay. Now I've got a stopper. Okay. Now, how come that stopper is not moving? How come the stopper is not moving right now? There's no reaction. There's no unbalanced force, UBF up the top there, right? So it's just doing what it's doing. So I'm going to come in here, and I've got a little handheld. It's kind of like the sparker that I just showed you, but it's going to give me a nice strong spark. The spark that comes off of this, or even the one I showed you before, is actually hotter than the surface of the sun on the inside. For real. In fact, if you rub your feet on a carpet and shock somebody, the little spark that flies off is actually hotter than the surface of the sun, but it's very, very, very narrow. Very, very, just a few atoms wide, but still. This thing is going to make a spark, and you'll be able to hear it, if not see it. You don't hear that up there? Okay. So you're see if I had something good metal up here, it maybe make it so you can see it. Oh, you hear it messing with the audio. Oh, that's cool. That thing as an electric field, I didn't even think about this. So I'm making an electric field that's messing with this microphone, I think. That's cool. Okay, so I'm gonna come here. Remember, this is pumping electrons into the end. They hate being near one another. They're as far apart as possible. They're going to jump into this bolt. They're going to jump across. They're going to make a little spark hotter than the surface of the sun. We've got alcohol inside. The cap on the top there is something that is not moving. And we come in here like this. Now, okay, so everybody wants me to do it again, right? I just hate to disappoint you because that's what happens when I try to do it again. Now, wait. Science, even when something doesn't work, is interesting. So I want you to think about why didn't it work. So first of all, before we do that, anybody know what it is that I just demonstrated that you've seen thousands of times today already? Evidence of thousands of times today. And this explosion has happened in your midst, in the red over there. Well, there is static electricity in your life, but you haven't seen that much static compared to what we just saw. And there's something else. Yes. Say again. Sun rays. Yeah, you've seen sun. Folks up there, just so you know what it was. Any ideas? What are you about to go do? What are you, all of you, what are you about to go do? Go home in a bus. You're going to see cars. This is how a car engine works. Just as you're walking out, just so you know, what do you think the liquid is in the bottom? Gasoline. What do you think the spark is in your car? The spark plug. What's this thing that flew out of the top? The piston. This is an internal combustion engine. Thank you all very much. So glad you came. So this is an internal combustion engine. Last question. Why did it not explode the second time around? Yes, ma'am. There's still alcohol in there, but there's something else we need. Well, look up here. What do we need for a flame? Oxygen. We actually used the oxygen and turned it into carbon dioxide. This thing would have to get new oxygen inside before it would burn a second time. Your car has an air filter. The air filter allows new oxygen in to burn the gasoline, and the gasoline actually has in it alcohol. You ever see that on a pump? It says may contain up to 10% ethanol. That's this stuff. I wanted to make stickers for a long time that said may contain up to 10% yeast pea and put them on all the pumps in Boone. Then I realized there were cameras at all the gas stations for people who drive away, and I knew I'd get arrested. So I decided not to do it. But if you all look on every gas pump and imagine this day and go, oh, I will translate what's on that pump to yeast pea instead of ethanol, you will know something a little bit more. Now, before we go, I want to just ask you the question, why did the top blow off? Yes. Why pressure? Okay, you're good, the flame, but I want you to look. Whatever is bigger, it made the air expand and it blew that top up. In a car, this thing's connected to a crankshaft. The cork flies off and it turns the crankshaft, and the next one turns it again a little bit more. But that's how a car, this isn't like, oh, and then he pretended to show us how a car engine works. This is how a car engine works. And that's the thing about the science around you and the science you're learning in your class. It's not just made up. It's not just a story that just somebody made up. It's stuff that explains the world around you. And it doesn't just explain the physical world. It helps you deal with the political world, because this is related to climate change and how we have to think through, gosh, are we going to burn fossil fuels that have trapped carbon dioxide from thousands, millions of years ago, and bring, and how is that going to change the climate, and is it worth doing it? How's that going to affect human beings? It's all connected, and you might end up writing poetry about it. It's connected to poetry. You might end up doing paintings about it. It's connected to art, and the art itself is using things like paints and clay, and those things themselves are scientific things. It's not like you drive down Science Street and turn onto Social Studies Street. It's all one street. And you use math to help figure out how it all works. It's all one thing. And one of the things I would love to do with you when you come to my class is help you start to see those connections. So 5, 6 years from now, I'll see you walking in these halls, and you all will be the ones up on the stage. Give my friends a hand here. Alexis, Jordan, Rebecca, and Howie. I hope you had a great day, and I look forward to seeing you around. Sorry.
Okay, how was that?